Nuclear fusion has potential beyond what you can imagine. It has the potential to power the stars. It can offer practically infinite energy with zero carbon emissions if it can be recreated on Earth. And unlike the current nuclear fission technology, nuclear fusion does not produce any long-term radioactive waste. For decades, the technology has appeared to be just out of reach, yet the reward is so great that billions of dollars continue to flow into the field. However, Germany's foremost plasma research facility has set a new record with its new nuclear fusion reactor, demonstrating that we are moving closer to the wonderful objective of fusion power, an almost endless source of clean, renewable energy. What is this new nuclear fusion reactor and what does it do? Also, when compared to the pioneering ITER reactor, how does this reactor stack up? The effort to develop a nuclear fusion reactor capable of creating abundant, sustainable energy, or to imitate the sun, has taken another step ahead. For physicists, fusion has been a type of holy grail. It has the potential to be a source of safe, clean nuclear energy if successfully exploited. Fusion connects atoms rather than separating them as nuclear fission reactors do. Thus, no hazardous radioactive waste is produced. Scientists at Germany's Max Planck Institute for Plasma Physics turned on an experimental reactor and produced hydrogen plasma in a device. This device is called the Wendelstein 7X stellarator. The stellarator is made to hold plasma formed by smashing hydrogen atoms together and blasting them with microwaves until the matter reaches temperatures of 100 million degrees, at which point the nuclei of the atoms fuse to form helium. The entire process generates energy and reflects what occurs at the sun's core. The stellarator's donut-shaped core, in essence, forms a miniature star. The device debuted in late 2015 at the Max Planck Institute for Plasma Physics, demonstrating that it could keep a loop of helium ions heated to 1,000,000 degrees in situ for a tenth of a second. The helium ions racing through the plasma reached a searing 40 million degrees Kelvin, 4 times hotter than in the following experiments when 18 times more energy was supplied into the W7X. As a point of reference, the sun's surface only reaches a temperature of 5,505 degrees Celsius. Do you see how powerful the stellarator is yet? While most of us are familiar with traditional nuclear energy, which is generated by the disintegration of large atoms, fusion energy is created when atoms are fused together. It's the most promising energy source of the future because it doesn't produce the same radiation troubles as atom-splitting power. Aside from the radioactive panels that line the reactor's interior walls, fusion is the cleanest kind of electricity generation. We must give them a big, forceful kick. That is something in the area of 100 million degrees of kicking, which necessitates a special type of machine. There are 2 types of these that are now promising, and W7X is one of them. The electromagnetic fields generated by the resultant plasma are used by machines like MIT's Alcator CMOD tokamak to help keep the writhing jelly donut of charged particles in line. With the hot, slam-dancing cloud of particles in place, fuel injection produces incredible amounts of energy. However, it's plagued by instabilities that make power generation a fleeting affair. Meanwhile, stellarators like the W7X use banks of magnetic coils to contain the plasma, giving them more control and allowing the hot ring of helium jelly to swirl for longer periods. Even though they don't quite match the output of the tokamak, W7X's 15-meter wide machine appears to have shown us a method to bridge that gap. The ITER nuclear reactor is another technology that is expected to usher in a new era of nuclear fusion power. ITER is the world's first and largest machine of its kind, currently being built at Cadarache, a French scientific research center specializing in nuclear power research. The machine would produce 500 megawatts of power by fusing 2 different types of hydrogen, referred to as deuterium and tritium. That's 10 times the amount of energy it would take to run. ITER, when finished, will have a diameter of 100 feet and a height of 100 feet, making it a new type of nuclear fusion device. It will be the world's largest magnetic confinement plasma physics experiment and the largest experimental tokamak nuclear fusion reactor when the reactor and first plasma are completed in late 2025. In the same way that a tokamak uses huge superconducting magnets to suspend hydrogen plasma and heat it to the temperatures and pressures required to fuse the material into helium, a stellarator does the same. The Wendelstein 7X is made up of 50 superconducting magnet coils that are approximately 3.5 meters tall. Instead of the torus or donut shape of a tokamak, the stellarator locks the plasma in a twisting and spiraling configuration. The electrons and ions in a tokamak are induced to flow around the tube as an electric current by a transformer-like arrangement. This current forms a vertical looping magnetic field which, when combined with the field already running the length of the tube, produces the spiraling field lines required. However, the tokamak is better at retaining a plasma than the other. To some extent, this is because the symmetry of a tokamak allows particles to follow smoother pathways. It is common for large numbers of microscopic particles to be lost in stellarators due to the large number of wiggles and ripples they encounter. This has led to a large majority of fusion studies since the 1970s, culminating in the massive ITER reactor project. With the addition of graphite tiles to the Wendelstein 7X's internal wall, higher temperatures can now be achieved. This inside liner, called a diverter, protects the twisting chamber walls while also allowing operators to pump more plasma in at greater temperatures, giving them more control over the hydrogen plasma density and purity. The Wendelstein 7X stellarator has been optimized to show that power facilities using stellarator-type fusion reactors are feasible. In order to overcome the drawbacks of previous stellarators, a tremendous deal of theoretical and computational effort was put into designing the magnetic field that keeps the heated plasma contained and away from the vessel's sides. One of the primary objectives was to limit the plasma's energy losses due to the magnetic field's ripple. Despite being bound to the magnetic field lines, plasma particles drift outwards and are lost as a result of this. Tokamaks, on the other hand, have modest losses owing to magnetic field ripple because of their symmetrical structure. Small vortex motions in the plasma, as well as turbulence, which is also incorporated as a loss channel in stellarators, affect the energy losses here. As a result, lowering neoclassical losses is an important task for stellarator optimization in order to catch up with the tokamak's good confinement properties. As a result, Wendelstein 7X's magnetic field was engineered to reduce those losses. Wendelstein 7X has already been able to generate high-temperature plasmas and set the stellarator world record for the fusion products at high temperature using the heating equipment available thus far. This combination of temperature, plasma density, and energy confinement duration shows how near you can come to the values for a burning plasma. Analysis of such a record plasma has now been completed in great detail. Although turbulent losses were negligible at these high plasma temperatures, neoclassical losses accounted for 30% of the heating power, making them a significant contributor to the energy balance. A thought experiment has now demonstrated the effect of Wendelstein 7X neoclassical optimization. It was anticipated that in plants with a less optimized magnetic field, the same plasma values and profiles led to the record achievement in Wendelstein 7X were also attained. Then the projected neoclassical losses were computed, yielding a clear result. They would be more than the input heating power, which is physically impossible. This means that the plasma profiles seen in Wendelstein 7X are only possible under low neoclassical loss magnetic fields. The opposite is also true. Adjusting the Wendelstein magnetic field successfully reduced the neoclassical losses. Tokamaks, on the other hand, have significant disadvantages. A transformer can only drive a current across the plasma in brief pulses, which is insufficient for a commercial fusion reactor. Current in the plasma can sometimes falter abruptly, causing disruptions, which are rapid losses of plasma confinement that can unleash magnetic forces strong enough to damage the reactor. Even newer designs like the spherical tokamak are plagued by such issues. Stellarators, on the other hand, are exempt. As there is no circulating plasma current, the fields generated by external coils do not need to be pulsed. Some teams have stuck with the concept because of these two factors. The power generated is virtually clean because the reactor does not produce heat by splitting atoms in a controlled nuclear reaction. Even though the Wendelstein 7X would not produce energy on its own, it will eventually be used to create a stellarator reactor that can run indefinitely. moving us closer and closer to a world of almost limitless energy provided by the same process that drives the sun. Let us know what you think of the nuclear reactor in the comments section below.